What if I told you that somewhere in the vast cosmic ocean, there exists a world with a 99.7% chance of hosting life? Not just a spark of microbial existence, not just a hint of water, but a planet that, based on cutting-edge observations, stands as one of the most promising candidates for extraterrestrial life ever discovered. This is no science fiction claim, no extrapolation from distant theories. It comes from the most sophisticated instruments humanity has ever built, the James Webb Space Telescope, the crown jewel of space observation, which peers deeper into the cosmos than any human eye has ever seen. The planet in question, K2-18b, has captured the attention of scientists, journalists, and stargazers alike, and the implications of this discovery could reshape everything we understand about life, the universe, and our place within it. At first glance, a probability like 99.7% seems almost absurd. To put it into perspective, it's far more certain than any prediction for discovering life on Mars or the moons of Jupiter or Saturn. It's almost like having a cosmic guarantee, an overwhelming indication from multiple lines of evidence suggesting that this planet could harbor life in a form we may understand, or even in ways that challenge our imagination. The number alone, 99.7%, forces the question, what does this mean for humanity? Could we finally be standing on the threshold of a discovery that answers the age-old question, are we alone? The intrigue doesn't stop there. This isn't a barren, rocky exoplanet bathed in sunlight like Venus or scorched like Mercury. K2-18b is special, mysterious, and uniquely poised in a sweet spot between potential habitability and the exotic conditions of alien worlds. It sits quietly, 120 light-years away, in the constellation Leo, a distant speck that has suddenly become the most talked-about world beyond our solar system. Every detail we've gathered, from its atmospheric composition to the subtle hints of oceanic presence, has been pieced together with painstaking precision, giving astronomers enough confidence to assert the staggering 99.7% probability of life. But why is this probability so high? And what does it mean to have a planet classified in this extraordinary way? This number isn't arbitrary. It's derived from the combined weight of spectral data, atmospheric modeling, and comparisons with what we know about Earth's own life-supporting chemistry. The implications are electrifying. If life exists there, even in microbial form, it could provide a template for how life emerges elsewhere in the universe. It could inform astrobiology, guide future missions, and forever change how we approach the search for life. This opening claim is not just a sensational hook, it's a challenge to every preconceived notion about life beyond Earth. It asks us to reimagine the possibilities of biology, to extend our understanding of planetary environments, and to reconsider the scale and scope of habitability. Scientists are cautious, of course, because extraordinary claims require extraordinary evidence, but the data from K2-18b is pushing them toward optimism. The more we study this planet, the more it defies the traditional expectations of exoplanetary science. It's not a cold, inhospitable rock. It's a world brimming with potential, a Hycean realm that could be teeming with life beneath its clouds. And here is the real hook for the audience. The 99.7% figure doesn't merely whisper of distant possibilities. It shouts a tantalizing promise that life might not just exist elsewhere in the universe, but that it may already have left detectable traces that we can study today. For humanity, for science, and for the very nature of our curiosity, this is a moment that could redefine everything. Are we on the verge of confirming that life is not a rare accident, but a cosmic principle? K2-18b might just be the answer, or at the very least, a window into answers that we have long sought. K2-18b may be light years away, but it has rapidly become one of the most compelling worlds ever discovered. Situated about 120 light-years from Earth, it orbits a red dwarf star known as K2-18, a relatively calm and stable star compared to its more temperamental stellar siblings. Red dwarfs are smaller and cooler than our Sun, which means their habitable zones, the regions where temperatures allow liquid water to exist, are much closer to the star. K2-18b occupies this sweet spot, giving it one of the most promising positions for potentially life-supporting conditions ever recorded. Discovered in 2015 by the Kepler Space Telescope during its K2 mission, K2-18b was initially identified through the transit method. This technique measures tiny dips in a star's brightness as a planet passes in front of it, allowing astronomers to calculate the planet's size, orbit, and sometimes even hints of its atmospheric composition. The initial data indicated that K2-18b was a super-Earth or mini-Neptune, a planet larger than Earth but smaller than Neptune, a type of exoplanet that is common in our galaxy but absent in our own solar system. Its size alone sparked interest, but it was the hints of an atmosphere that turned this discovery into a potential breakthrough in the search for extraterrestrial life. K2-18b orbits its star every 33 days, keeping it close enough to maintain temperatures that could allow for liquid water, yet far enough to avoid being scorched. Its proximity to its star places it in a delicate balance, often referred to as the habitable zone, which has made it the centerpiece of countless studies and simulations. Unlike many planets around red dwarfs that are bombarded by intense flares, K2-18's relatively calm nature increases the chances that an atmosphere, and possibly life, could survive for billions of years. What makes K2-18b even more intriguing is that it exists in a stellar neighborhood that is accessible to observation. Being only 120 light-years away in the Leo constellation means that, in cosmic terms, it is practically our backyard. While that distance is still beyond human travel for the foreseeable future, it is close enough for instruments like the James Webb Space Telescope to gather detailed spectral data about its atmosphere. Researchers can analyze the light that passes through the planet's atmosphere as it transits its star, revealing chemical signatures that hint at water vapor, methane, carbon dioxide, and potentially even biomarkers of life. The discovery of K2-18b also represents a turning point in exoplanetary science. Before this planet, many super-Earths and mini-Neptunes were catalogued, but few had atmospheric data compelling enough to suggest habitability. K2-18b was different. Early observations with the Hubble Space Telescope indicated the presence of water vapor in its atmosphere, a finding that immediately elevated its status from a generic exoplanet to a leading candidate in the search for extraterrestrial life. Its combination of size, position, and atmospheric properties created a rare opportunity, a planet that is not only detectable but analyzable, giving scientists a chance to study habitability in a context remarkably different from Earth while retaining some familiar conditions. In short, K2-18b is a planet that bridges the gap between the familiar and the alien. It orbits a relatively calm star, sits squarely in the habitable zone, and has atmospheric characteristics that can be scrutinized with current technology. Its discovery history, from Kepler's initial detection to subsequent Hubble observations, sets the stage for an unprecedented era of study, one where the tantalizing possibility of life moves from the realm of speculation to testable science. Every detail about its location and discovery contributes to the growing excitement, positioning K2-18b as a cornerstone in humanity's quest to answer the ultimate question: is life elsewhere in the universe possible, probable, or even inevitable? K2-18b isn't just another exoplanet orbiting a distant star. It belongs to a class of planets that scientists have only recently begun to understand, known as Hycean worlds. The term Hycean comes from a combination of hydrogen and ocean, describing planets that possess vast oceans beneath thick, hydrogen-rich atmospheres. Unlike Earth, where nitrogen and oxygen dominate our sky, Hycean planets are enveloped in a deep layer of hydrogen and helium, making their atmospheres far denser and more massive than what we experience at home. This dense atmosphere doesn't just provide pressure, It acts like a thermal blanket, trapping heat and potentially keeping surface or oceanic temperatures within a range that allows liquid water to exist, even at distances from their stars where traditional habitability models would predict freezing conditions. The concept of a Hycean world is transformative because it expands the traditional definition of habitability. For decades, scientists focused primarily on Earth-like planets, rocky worlds with thin atmospheres, temperate climates, and liquid water on the surface. Hycean worlds challenge that narrow view. On these planets, oceans may extend hundreds of kilometers below the atmosphere, far deeper than any ocean on Earth, and the chemistry of these oceans could support life forms radically different from those we know. The hydrogen-rich skies can mix with chemical compounds dissolved in the oceans, creating potential energy sources that life could exploit, much like microbes around hydrothermal vents on Earth. K2-18b in particular exemplifies the Hycean model. Its size, about 2.6 times the radius of Earth, and mass, roughly 8 times that of our planet, suggest a strong gravitational pull capable of holding onto a thick atmosphere. Observations indicate that this atmosphere is dominated by hydrogen, with traces of water vapor and other molecules like methane and carbon dioxide. Beneath that envelope, scientists hypothesize an ocean world where liquid water could exist under immense pressure, warmed by both the greenhouse effect of the hydrogen and potential internal heat sources from the planet's interior. One of the most exciting aspects of Hycean worlds is the potential for habitability under conditions that were once considered inhospitable. Traditional models of life focus on surface conditions resembling Earth's shallow oceans and temperate climates. But in a Hycean world, life might exist hundreds of kilometers beneath the thick atmosphere, thriving in oceanic environments where sunlight is minimal, but chemical energy is abundant. These oceans could harbor microbial ecosystems, complex chemical networks, and perhaps even larger life forms adapted to high-pressure, hydrogen-rich environments. The concept stretches our imagination, allowing us to envision life thriving in environments utterly alien, yet fundamentally bound by the universal requirements of liquid water, energy, and chemical nutrients. K2-18b's status as a Hycean planet also means it could be among the most detectable habitable worlds beyond Earth. Because the planet's hydrogen-rich atmosphere is transparent enough in some wavelengths, instruments like the James Webb Space Telescope can probe it for chemical signatures, potentially even detecting biomarkers or molecules that could indicate life. This is precisely why K2-18b has become such a central figure in astrobiology. It combines theoretical habitability with observational accessibility, a rare and tantalizing combination in the search for life beyond Earth. In essence, Hycean worlds like K2-18b redefine what it means for a planet to be habitable. They show us that life might not require an Earth twin, that it can thrive under alien skies and in oceans deeper than any we can imagine, and that the universe could be far more biologically rich than we have ever dared to consider. By identifying and studying these worlds, humanity may be approaching a future in which discovering life elsewhere becomes not just a possibility, but a plausible expectation. K2-18b stands out in a way that few exoplanets ever have. The sheer combination of its size, orbit, atmospheric composition, and proximity to Earth makes it a singular target in the search for life. While thousands of exoplanets have been discovered since the 1990s, most of them fall into categories that either make them inhospitable or impossible to study in detail. Many are gas giants like Jupiter or Neptune, orbiting far from their stars, or too close and scorched by stellar radiation, while others are small, rocky worlds that offer little to no atmosphere for scientists to probe. K2-18b, in contrast, occupies a rare intersection of conditions that make it both potentially habitable and observable. Most exoplanets identified before K2-18b were either too massive, too hot, or too cold. Hot Jupiters, for instance, are gas giants that orbit perilously close to their stars, experiencing temperatures of thousands of degrees, and while their atmospheres can be studied, they are too extreme to support life as we know it. On the other end, many rocky super-Earths orbit in colder regions, with atmospheres too thin or too frigid to maintain liquid water. K2-18b, however, sits comfortably in the habitable zone of its star, where temperatures are theoretically suitable for liquid water to exist beneath its thick, hydrogen-rich atmosphere. Its size, roughly 2.6 times the radius of Earth, allows it to maintain a dense atmosphere without collapsing under gravity or losing volatile gases to space, a balance that is rare among discovered exoplanets. Another reason K2-18b stands out is the detection of water vapor in its atmosphere, something that only a handful of exoplanets have revealed so far. While Hubble previously detected water on a few distant worlds, these were often isolated measurements, uncertain and lacking detailed context. K2-18b offered repeated opportunities for observation, allowing astronomers to confirm the presence of water and even identify other molecules like methane and carbon dioxide. This makes it the first super-Earth or mini-Neptune where habitability indicators are not just theoretical, but measurable. Its Hycean nature further separates it from other studied planets. While many super-Earths and mini-Neptunes are presumed to be inhospitable gas planets, K2-18b's combination of ocean potential, hydrogen-rich atmosphere, and stable stellar environment allows for a plausible scenario where life could emerge. This is distinct from planets like GJ1214b, a well-known mini-Neptune with a hydrogen-rich atmosphere, but one that appears too hot and turbulent to support stable oceans. K2-18b strikes a rare equilibrium where the physical and chemical conditions converge toward potential habitability. Moreover, its proximity in the Leo constellation makes it highly accessible to the most advanced observational technology, including the James Webb Space Telescope. Many potentially habitable planets lie hundreds or even thousands of light-years away, making detailed atmospheric analysis impractical. K2-18b, being just 120 light-years distant, provides a unique opportunity. It is close enough for us to detect subtle chemical signatures, yet distant enough that it remains largely unaffected by observational noise and interference. This combination of habitability, detectability, and accessibility is unprecedented among the catalogue of known exoplanets. In essence, K2-18b represents a rare convergence of factors that make it exceptional. Unlike countless other worlds that are either too extreme, too distant, or too opaque to study, it offers a window into the potential for life in environments fundamentally different from Earth. Its discovery has shifted the paradigm of exoplanet science, demonstrating that habitable conditions can exist in forms previously unimagined, and that life may not be limited to Earth-like planets with nitrogen-oxygen atmospheres. K2-18b is more than just another dot in the sky. It is a leading candidate for the most profound discovery in human history, the possibility that life exists beyond our planet. The James Webb Space Telescope has fundamentally changed the game when it comes to studying exoplanets, and K2-18b is one of its most compelling targets. Unlike previous telescopes, Webb possesses a combination of sensitivity, infrared range, and spectroscopic power that allows scientists to examine planetary atmospheres in unprecedented detail. While Hubble provided initial hints of water vapor on K2-18b, it could only scratch the surface. Webb, with its advanced instruments like the Near-Infrared Spectrograph, NIR-SPEC, and Mid-Infrared Instrument, MIRI, can detect faint chemical signatures that reveal not only the presence of molecules, but also their concentrations, vertical distribution, and even hints about cloud cover and weather patterns. Webb's infrared capabilities are crucial because many molecules, including water, methane, carbon dioxide, and dimethyl sulfide, absorb light in the infrared range. As K2-18b passes in front of its star, some of the starlight filters through the planet's atmosphere, leaving behind a chemical fingerprint. Webb captures this light and disperses it into a spectrum, showing peaks and troughs corresponding to specific molecules. This method allows astronomers to not just detect water, but to identify the combination of gases in the atmosphere, a process known as transmission spectroscopy. By analyzing these signatures, scientists can determine the planet's potential habitability and even spot anomalies that might suggest biological processes. Another advantage of the James Webb Space Telescope is its ability to peer through thick atmospheres, something that has long been a challenge in exoplanet studies. K2-18b's dense hydrogen-rich envelope previously made it difficult to detect the subtler chemical signals necessary to assess habitability. Webb's instruments, with unparalleled sensitivity and resolution, can differentiate between layers of atmosphere, detect trace molecules, and even hint at the presence of clouds or hazes that could obscure the surface or ocean beneath. For a Hycean world like K2-18b, this is revolutionary. Scientists can now construct three-dimensional models of its atmosphere, including temperature gradients, pressure levels, and chemical compositions, a level of detail that was unimaginable just a few years ago. Webb has also enabled continuous monitoring of K2-18b over multiple transits. By observing the planet repeatedly, astronomers can confirm the presence of molecules, detect seasonal or weather-related changes, and build a more comprehensive picture of its environment. This iterative observation is crucial for validating findings, ruling out false positives, and strengthening the statistical confidence behind bold claims, like the staggering 99.7% chance of life. Previous telescopes lacked this combination of sensitivity, spectral coverage, and observing flexibility, making Webb the first instrument capable of moving from speculative detection to detailed, actionable data about exoplanetary atmospheres. The telescope's contribution goes beyond mere detection. By revealing hidden details, such as the relative abundance of gases, the potential for clouds, and even temperature variations at different altitudes, Webb allows scientists to construct hypotheses about surface or oceanic conditions. This means that K2-18b is no longer a distant point of light in a telescope, but a complex, layered world whose atmospheric chemistry and potential habitability can be studied with unprecedented accuracy. Each observation brings us closer to answering questions that were once purely theoretical. Does this planet have liquid water beneath its hydrogen-rich skies? Could it support microbial life? Are there chemical signatures that suggest biological activity? In short, the James Webb Space Telescope has transformed K2-18b from a promising candidate into a prime laboratory for studying alien life. Its advanced instruments reveal the invisible, detect the faintest traces of molecules, and provide the high-resolution spectra that allow scientists to make confident predictions about habitability. Without Webb, the 99.7% figure for potential life would remain speculative at best, but with its data, astronomers can analyze, test, and refine their understanding of what is arguably the most extraordinary exoplanet discovery of our time. The atmosphere of K2-18b is nothing short of extraordinary. While its classification as a Hycean world already suggested the presence of a thick hydrogen-rich envelope and potentially vast oceans beneath, the James Webb Space Telescope has turned those hypotheses into observable data, uncovering atmospheric clues that hint at habitability and perhaps even life itself. Among the most exciting discoveries are the detection of water vapor, methane, and carbon dioxide, molecules that play critical roles in Earth's own biosphere and are considered key indicators of habitability on exoplanets. Water vapor, in particular, has been a breakthrough. Hubble's earlier observations hinted at water in the atmosphere of K2-18b, but Webb's instruments provided spectral confirmation and quantification. By analyzing the starlight passing through the planet's atmosphere during transits, Webb detected absorption patterns that match the molecular fingerprints of water. These measurements suggest that the planet has a significant abundance of water vapor in its upper atmosphere, which could be linked to underlying oceans. The presence of water is crucial because on Earth, liquid water is the medium in which all life exists. On K2-18b, water may exist not just in the atmosphere, but potentially in massive subsurface oceans beneath hundreds of kilometers of hydrogen-rich air, providing an environment that could sustain life in forms entirely different from what we know. Methane, another molecule detected in K2-18b's atmosphere, is particularly intriguing because it can be produced through both geological and biological processes. On Earth, methane is emitted by both natural phenomena, such as volcanic activity, and by living organisms, including microbes in wetlands and oceans. Its presence on K2-18b raises exciting possibilities. While methane alone cannot confirm life, its detection in combination with other molecules, especially water and carbon dioxide, strengthens the argument that the planet's chemistry is active, dynamic, and potentially conducive to life. In a hydrogen-rich atmosphere like K2-18b's, methane could interact with water vapor and other compounds to form a complex web of chemical reactions, creating niches where life could thrive. Carbon dioxide adds another piece to this puzzle. On Earth, CO2 plays a critical role in regulating climate and maintaining the greenhouse effect, which keeps surface temperatures suitable for life. On K2-18b, the presence of carbon dioxide in the atmosphere could indicate a similar role. The gas may contribute to warming the planet, keeping the hypothesized oceans in a liquid state despite the distance from its star. Moreover, carbon dioxide interacts chemically with water and other compounds, potentially forming bicarbonates or other molecules that could provide nutrients for hypothetical oceanic life. These three molecules, water vapor, methane, and carbon dioxide, together create an atmosphere with chemical diversity, thermal regulation, and energy potential, forming a tantalizing template for habitability that scientists can now study in unprecedented detail. What makes K2-18b even more remarkable is the combination of these molecules in a Hycean environment. Unlike Earth, where the atmosphere is thin and dominated by nitrogen and oxygen, K2-18b's hydrogen-rich envelope exerts a high pressure that would make surface conditions extreme by terrestrial standards. Yet this high-pressure environment does not preclude life. In fact, it may be exactly the type of environment in which certain types of microbial life could thrive. The chemical interactions between hydrogen, water vapor, methane, and carbon dioxide may generate energy gradients and metabolic opportunities that could sustain ecosystems in the planet's hypothesized oceans, perhaps similar to the way life thrives near hydrothermal vents in Earth's deep oceans. Spectroscopic analysis from Webb has also allowed scientists to map the vertical distribution of these gases, revealing how they change with altitude. Water vapor appears in the upper layers of the atmosphere, while methane and carbon dioxide show patterns that hint at dynamic processes, including vertical mixing, potential cloud formation, and chemical cycling. These patterns are crucial because they indicate that K2-18b is not a static world. It is chemically active, with a complex interplay between atmospheric gases, clouds, and potentially the ocean beneath. This dynamism is a hallmark of planets capable of sustaining life, as life depends not only on the presence of molecules, but also on energy flows and chemical interactions that can drive metabolism. The implications of these atmospheric clues extend beyond habitability. They touch on the search for biosignatures, the chemical signs of life. On Earth, the simultaneous presence of water, methane, and carbon dioxide is often associated with biological activity, particularly when they exist in proportions that are out of equilibrium. Life tends to produce chemical imbalances, creating molecular signatures that persist in the environment. While the data from K2-18b do not yet confirm life, they provide the first strong observational evidence that this planet possesses the building blocks and environmental conditions where life could plausibly exist. Scientists can now model hypothetical biological processes, simulating how life might alter atmospheric chemistry over time. and compare these predictions to Webb's observations to look for inconsistencies or anomalies that suggest biological activity. Moreover, the detection of these molecules allows researchers to study the planet's climate and energy cycles. Water vapor, methane, and carbon dioxide interact with starlight, trapping heat, forming clouds, and driving potential weather systems. Webb's observations can detect variations in these molecules as the planet rotates, hinting at wind patterns, storm activity, and seasonal changes. Understanding these dynamics is critical because stable climate conditions are a prerequisite for life. Extreme fluctuations could sterilize oceans or prevent complex chemistry from forming, while moderate cyclical variations could promote a thriving biosphere. K2-18b's atmosphere appears to show signs of stability, adding another layer of optimism for its potential habitability. These atmospheric clues are the first step toward identifying more complex and rare molecules, including potential biomarkers like dimethyl sulfide, DMS, which Webb may be able to detect in future observations. The presence of water, methane, and carbon dioxide sets the stage for more detailed searches, establishing K2-18b as a prime laboratory for testing hypotheses about alien life in hydrogen-rich environments. Each molecule detected not only informs us about the planet's current conditions, but also allows scientists to infer its geological activity, ocean chemistry, and energy cycles, building a comprehensive picture of a world that is not merely a distant dot, but a dynamic, potentially life-bearing planet. One of the most intriguing aspects of K2-18b's atmosphere isn't what's present, it's what's missing. Despite the detection of water vapor, methane, and carbon dioxide, astronomers have noted a distinct absence of ammonia, NH3, a molecule that, in hydrogen-rich atmospheres, is often expected. Ammonia is a simple nitrogen compound that could naturally form under the chemical conditions predicted for Hycean worlds. Its absence provides a subtle but powerful clue about K2-18b's atmospheric chemistry, thermal environment, and potential habitability, and understanding why it is missing offers deep insight into the planet's suitability for life. On many hydrogen-rich planets, ammonia forms when nitrogen combines with hydrogen under moderate temperatures and pressures. It is chemically stable in cooler conditions, but tends to break down at higher temperatures or in the presence of ultraviolet radiation from the host star. K2-18b's red dwarf star emits relatively low levels of UV radiation compared to stars like our Sun, so scientists initially expected ammonia to survive in the atmosphere. Yet, careful spectral analysis from the James Webb Space Telescope shows no detectable ammonia, suggesting either that it is being actively destroyed or that it never accumulated in the first place. This raises several possibilities, each with profound implications for habitability. One explanation for ammonia's absence is that it may have been converted into other nitrogen-bearing compounds, such as nitrogen gas, N2, or even more complex molecules like nitrates or nitrites, through chemical reactions within the atmosphere or at the interface with the underlying ocean. On Earth, nitrogen cycles through the environment via complex pathways involving microbial life, geology, and atmospheric chemistry. While we cannot assume that K2-18b hosts life, the absence of ammonia may indicate that similar chemical cycling occurs, potentially driven by geochemical processes, ocean-atmosphere interactions, or even hypothetical biological activity. The lack of ammonia does not necessarily reduce the planet's habitability. In fact, it could suggest a dynamic, evolving atmosphere capable of supporting complex chemical networks, conditions that are essential for life. Another possibility is that ammonia is destroyed by photochemical reactions in the upper atmosphere. Even though red dwarfs emit less UV light, some ultraviolet and high-energy radiation still reaches the planet. In the hydrogen-rich atmosphere of K2-18b, ammonia could react with radicals or photodissociate under the influence of this radiation, breaking down into simpler compounds like nitrogen and hydrogen. This process might explain its absence and simultaneously hint at active atmospheric chemistry, a crucial ingredient for maintaining energy flows that could support life. Photochemistry can drive the formation of molecules that are biologically relevant or energy-rich, creating environments analogous to hydrothermal vents on Earth, where life thrives without sunlight. The absence of ammonia also influences the planet's greenhouse dynamics. Ammonia is a potent greenhouse gas, capable of trapping heat efficiently. Without it, the thermal profile of K2-18b's atmosphere may differ from earlier predictions, potentially creating more stable temperature ranges in the upper atmosphere and ocean beneath. This could be particularly favorable for life in the deep oceans, where excessive heating might disrupt chemical gradients necessary for metabolism. A more stable, moderated climate resulting from ammonia's absence may paradoxically enhance the habitability of K2-18b's Hycean environment. From an observational standpoint, the missing ammonia provides a valuable diagnostic tool. Scientists use the presence or absence of specific molecules to constrain atmospheric models and refine their understanding of chemical processes. For K2-18b, the lack of ammonia has already informed simulations of atmospheric circulation, temperature distribution, and potential ocean-atmosphere interactions. It suggests that the planet's environment is not static, but shaped by active chemistry, energy exchanges, and possibly surface or subsurface processes. Such dynamics are precisely what researchers look for when identifying planets capable of sustaining life. Interestingly, the absence of ammonia may also make K2-18b a better candidate for hosting life as we know it. On Earth, life has evolved in an environment where ammonia is scarce. Instead, nitrogen exists primarily as N2, which is converted biologically into usable forms like nitrates and ammonium through nitrogen fixation. If K2-18b's nitrogen is similarly locked in stable compounds rather than free ammonia, it could create chemical gradients suitable for hypothetical life forms in its oceans. In other words, ammonia's absence does not necessarily hinder the planet's potential for life. It may actually mirror certain aspects of Earth's own nitrogen chemistry, which has been central to the development of life. The absence of ammonia emphasizes the subtlety and sophistication of exoplanetary science. Habitability cannot be judged solely by the presence of water or other obvious molecules. Sometimes, the missing pieces tell as much of the story as what is detected. In K2-18b's case, ammonia's absence provides evidence for active, complex chemistry, moderate temperatures, and possibly even mechanisms that could support biological processes. It highlights that the planet is not a simple, unchanging sphere, but a dynamic world with a chemical and potentially biological narrative waiting to be deciphered. One of the most electrifying developments in the study of K2-18b is the potential detection of dimethyl sulfide, or DMS, in its atmosphere. This molecule has become a focal point in astrobiology because of its strong association with life on Earth. Unlike water vapor or carbon dioxide, which can be produced through geological or chemical processes without life, DMS is almost exclusively a biogenic molecule, meaning that on our planet, it is produced nearly entirely by living organisms. Its potential presence on K2-18b has sent ripples through the scientific community because it could represent one of the clearest, most direct chemical hints of extraterrestrial life ever observed. Dimethyl sulfide is a sulfur-containing compound that originates from the metabolism of phytoplankton in Earth's oceans. These tiny organisms break down dimethyl sulfonneopropionate, DMSP, a protective chemical to release DMS into the atmosphere. From there, DMS plays a role in cloud formation, influencing Earth's climate, and it contributes to the planet's sulfur cycle. The significance of DMS in astrobiology lies in the fact that its atmospheric signature is highly unusual in abiotic contexts. While certain geological processes can produce sulfur compounds, the specific concentration, distribution, and isotopic ratios of DMS found in a planetary atmosphere are extraordinarily difficult to replicate without biology. If Webb or future telescopes detect DMS in the atmosphere of K2-18b, it could serve as a strong biosignature, a molecule whose presence would be difficult to explain without life. This is what makes it different from molecules like methane, which can be both geological and biological. In a hydrogen-rich Hycean atmosphere, the presence of DMS would suggest ongoing biological activity beneath the clouds, likely in the hypothesized global oceans. Unlike surface life that interacts directly with sunlight, life-producing DMS could thrive in deep, oceanic environments, releasing sulfur gases that eventually diffuse into the atmosphere. The potential discovery of DMS is particularly important for Hycean worlds like K2-18b because these planets have deep oceans covered by thick, hydrogen-rich atmospheres, making traditional surface observations impossible. Detecting DMS in the atmosphere could provide a rare and direct glimpse into the chemical output of subsurface life, giving scientists one of the few observational tools to infer biology on an alien planet without physically visiting it. The fact that DMS can rise from an ocean and survive transit through a thick atmosphere into the upper layers makes it uniquely valuable as a biomarker in these environments. Moreover, the search for DMS requires the advanced sensitivity and spectral resolution of instruments like JWST's NIR spec and MIRI, capable of detecting subtle absorption features in the infrared spectrum. These instruments can differentiate DMS from other sulfur-containing molecules and identify it against the backdrop of hydrogen, methane, water vapor, and carbon dioxide. Its spectral signature, though faint, is distinct and recognizable to astronomers, allowing for rigorous testing of its presence. Multiple observations over successive transits would be needed to confirm DMS and rule out non-biological sources, but even the hint of it has already generated intense excitement. Detecting DMS would also provide critical insight into the types of ecosystems that might exist on K2-18b. On Earth, DMS production is intimately tied to marine microbial life, particularly phytoplankton, which forms the base of oceanic food webs. If DMS exists on K2-18b, it could indicate a similarly complex oceanic ecosystem, with life adapted to the high-pressure, hydrogen-rich conditions of a Hycean world. While these organisms would almost certainly be microbial, their chemical activity could have planet-wide consequences, shaping the atmosphere in ways that are observable from Earth, a remarkable bridge between alien life and detectable planetary signals. The detection of DMS would also dramatically elevate the statistical probability that K2-18b harbors life. While the earlier 99.7% figure is based on general atmospheric chemistry, habitable temperature ranges, and ocean potential, the presence of DMS would represent a direct biosignature, not just a probabilistic inference. It would turn theoretical habitability into a tangible, evidence-based claim, providing a benchmark for the first confirmed detection of life beyond Earth. However, the scientific community remains cautious. DMS is not entirely impossible to form through abiotic chemistry, though it is extremely rare. Planetary scientists are developing models to determine whether K2-18b's atmosphere could generate DMS without biology, and so far, the consensus is that non-biological production would be minimal and unlikely to account for significant concentrations. This makes DMS a high-priority target for continued observations and one of the most promising biomarkers in exoplanetary science. In essence, dimethyl sulfide is a molecule that could redefine humanity's understanding of life in the universe. While water, methane, and carbon dioxide hint at habitability, DMS could indicate active biology in an alien ocean, detectable from over 100 light-years away. Its potential discovery positions K2-18b not just as a fascinating exoplanet, but as the first world where we might witness the fingerprints of extraterrestrial life, offering a bridge from speculation to scientific confirmation. Dimethyl sulfide, or DMS, is one of the most fascinating molecules when considering the search for life beyond Earth, largely because of its unique role on our own planet. On Earth, DMS is almost entirely a product of biological activity, specifically from marine microorganisms. Phytoplankton, tiny photosynthetic organisms in the ocean, produce a chemical called dimethyl sulfonopropionate, DMSP, as part of their metabolic processes. This compound helps protect these organisms from environmental stresses, such as changes in salinity or light intensity. When DMSP breaks down, either naturally in the water or through the activities of bacteria, it produces DMS, which then escapes into the atmosphere. The result is a direct chemical link between microscopic life in the oceans and the composition of Earth's atmosphere. What makes DMS so remarkable is that it is nearly biologically exclusive. While there are a few ways sulfur compounds can form through purely geological or chemical processes, producing DMS at concentrations comparable to those generated biologically is extremely rare. This gives scientists a unique advantage. If they detect significant amounts of DMS in a planetary atmosphere, it is strong circumstantial evidence that some form of life may be active on that world. On Earth, DMS is intricately tied to ecological systems and even planetary climate. When released into the atmosphere, it contributes to cloud formation by acting as cloud condensation nuclei, indirectly influencing climate patterns. This interplay between biology and planetary systems makes DMS not only a biosignature, but also a molecule that highlights the interconnectedness of life and planetary habitability. The Earth connection provides a concrete reference point for interpreting observations of K2-18b. When astronomers detect DMS in the atmosphere of this distant Hycean world, they can draw on decades of terrestrial data to understand what that molecule might represent. The presence of DMS suggests active metabolic processes, likely in an ocean environment, producing gases that diffuse upward through the thick, hydrogen-rich atmosphere. Even if the life on K2-18b is entirely unlike anything on Earth, the biochemical requirement to release DMS, or a similar sulfur-containing gas, creates a parallel that allows scientists to infer biological activity in an alien setting. Moreover, the exclusive association of DMS with life on Earth strengthens its value as a biosignature because it reduces the likelihood of false positives. Unlike methane, which can arise from volcanic activity, or water vapor, which is widespread and abiotic, DMS is rare in non-biological contexts. Its detection in a planetary atmosphere would be a striking anomaly, immediately drawing attention as a potential signal of life. In essence, Earth acts as a model, the molecule that connects microbial activity in oceans to the atmospheric chemistry observable from space shows how life, even at microscopic scales, can leave detectable fingerprints at planetary levels. This connection also underscores why K2-18b is such a unique target. Its hypothesized global ocean beneath a hydrogen-rich atmosphere mirrors conditions on Earth at a conceptual level, even if the chemistry is vastly different. On our planet, DMS production occurs in shallow, sunlit oceans, but K2-18b's life, if it exists, might operate deep beneath thick atmospheric layers in conditions of high pressure and limited light. Despite these differences, the basic principle remains the same. Life interacts with its environment in a chemical feedback loop, and certain molecules like DMS can escape the local habitat to become detectable at planetary scales. This suggests that even alien life could leave chemical clues analogous to the ones we observe on Earth. The Earth connection also emphasizes the broader implications of detecting DMS elsewhere. On our planet, DMS is not just a molecule, it is a marker of a living, functioning ecosystem. Its detection on K2-18b could therefore imply the presence of entire oceanic ecosystems, microbial networks, and energy cycles that are actively maintaining themselves. This shifts the search for life from a binary question, does it exist or not, to a nuanced investigation into the complexity and dynamics of alien biospheres. DMS, in this sense, becomes a window not just into life itself, but into the environmental and ecological processes that make a planet habitable over long timescales. The Earth connection provides a framework for future exploration. By studying how DMS behaves in our atmosphere, its production, transport, degradation, and interaction with other compounds, scientists can build predictive models for K2-18b. They can estimate the concentration needed for detection, understand how the molecule might behave in a hydrogen-rich environment, and anticipate the spectral signatures that Webb and subsequent telescopes should look for. Essentially, Earth serves as both a laboratory and a guidebook, offering a roadmap for interpreting what could be the first tangible signs of life beyond our planet. K2-18b presents a tantalizing picture when it comes to surface conditions, and understanding these parameters is critical for evaluating the planet's potential to harbor life. Unlike Earth, we cannot physically visit or measure K2-18b directly, so scientists rely on a combination of observational data from telescopes like James Webb, theoretical modeling, and analogues from planetary science to reconstruct what this alien world might be like. What emerges is a planet that is at once familiar and profoundly alien, a Hycean world with hydrogen-rich skies and deep oceans, yet subject to pressures, temperatures, and chemical dynamics that challenge human intuition. Starting with temperature, K2-18b resides within the habitable zone of its red dwarf star in the Leo constellation, approximately 120 light-years from Earth. This zone, often referred to as the Goldilocks zone, is where temperatures are theoretically conducive to liquid water. Webb's observations of atmospheric composition, including water vapor, methane, and carbon dioxide, help scientists infer thermal properties. Models suggest that K2-18b could maintain surface or ocean temperatures ranging from roughly 0 degrees to 50 degrees, depending on altitude, depth, and heat flux from the interior. This is slightly warmer than Earth's average, but still within ranges that life could plausibly tolerate, particularly microbial life. The planet's thick hydrogen-rich atmosphere also acts as a greenhouse blanket, trapping heat and stabilizing temperature fluctuations. Unlike Earth, which experiences significant temperature variation between day and night or across seasons, K2-18b may have a more homogenized climate, with atmospheric circulation distributing heat across the planet. Clouds, composed possibly of water droplets or more exotic condensates, could further modulate temperatures by reflecting starlight and maintaining a balance between heating and cooling. These dynamics suggest a world that, while alien, could sustain relatively stable environmental conditions, a prerequisite for life to emerge and persist over geological timescales. Beneath this thick atmosphere lies the hypothesized ocean, which could extend hundreds of kilometers deep, far surpassing the deepest regions of Earth's oceans. The sheer depth would create extreme pressures at the ocean floor, far greater than any life on Earth has experienced in natural conditions. Yet, studies of Earth's extremophiles, microorganisms living in deep-sea hydrothermal vents or subglacial lakes, demonstrate that life can adapt to high pressures and limited light if energy sources are available. On K2-18b, chemical gradients between hydrogen, methane, water, and carbon dioxide could serve as these energy sources, powering metabolism for hypothetical oceanic organisms. Life might utilize chemosynthesis, analogous to deep ocean microbes on Earth, extracting energy from chemical reactions rather than sunlight, allowing ecosystems to thrive in perpetual darkness beneath the hydrogen-rich skies. Energy on K2-18b could also be supplemented by internal planetary heat. As a relatively massive super-Earth, about 8 times the mass of Earth, K2-18b likely experiences significant geothermal activity, driven by radioactive decay and residual heat from planetary formation. This internal heat could drive hydrothermal vents at the ocean floor, creating localized environments rich in chemical energy. These vents could produce gradients of sulfur, methane, and other compounds, offering life potential niches where it can flourish independently of sunlight. Coupled with convective currents in the deep oceans, these energy flows could sustain dynamic chemical ecosystems, providing continuous energy input for potential biological activity. The interplay between the thick atmosphere and underlying ocean also influences surface conditions. Hydrogen-rich atmospheres at high pressure create conditions where liquid water could exist even at temperatures slightly above Earth's boiling point because of pressure-dependent boiling points. This means that K2-18b's oceans could remain liquid over a wider range of temperatures than Earth's, further expanding the habitable zone. Additionally, the dense atmosphere could shield the ocean from harmful cosmic radiation and stellar flares, which are common in red dwarf systems, allowing life to exist in relative safety beneath the protective blanket of gas. While we cannot yet confirm the exact chemistry of K2-18b's surface and oceans, models suggest the presence of nutrient cycles similar to Earth's, facilitated by interactions between the ocean and atmosphere. For example, methane produced in the ocean could diffuse upward, reacting with atmospheric components, while water vapor participates in condensation and cloud formation, creating a feedback loop of energy and chemical flux. These processes could maintain long-term stability, making K2-18b a promising candidate for sustained habitability rather than a transient or marginally habitable environment. Importantly, surface conditions also impact the detectability of life. The combination of hydrogen-rich atmosphere, ocean depth, and chemical cycling allows molecules like DMS, methane, and water vapor to enter the upper atmosphere, where instruments like Webb can detect them. This means that K2-18b's unique structure, thick atmosphere over deep oceans, could facilitate the remote sensing of biosignatures, essentially broadcasting the potential existence of life from beneath the clouds to distant observers, a concept that is almost unprecedented in planetary science. In summary, K2-18b's surface conditions paint a picture of an alien ocean world with moderate, life-supporting temperatures, immense oceans under high pressure, and rich sources of chemical energy. While humans would not survive on the surface without extreme technological intervention, these conditions are remarkably favorable for hypothetical life forms adapted to the environment. From the protective hydrogen-rich atmosphere to the deep oceans warmed by stellar and internal energy, K2-18b embodies a complex system where biology, chemistry, and planetary physics could converge in ways that mirror, yet also diverge dramatically from, Earth's life-supporting conditions. K2-18b's atmosphere is one of the most fascinating aspects of this alien world, and the James Webb Space Telescope has provided unprecedented insight into what its skies might look like. Unlike Earth, where clouds are composed primarily of water droplets or ice crystals, K2-18b's hydrogen-rich atmosphere suggests clouds could form from a variety of exotic compounds, depending on temperature, pressure, and chemical composition. Webb's advanced infrared instruments have allowed astronomers to detect signatures indicating the presence of thick, layered clouds, which play a crucial role in regulating the planet's climate, distributing heat, and potentially influencing habitability. The observations suggest that K2-18b may have dynamic weather systems, with clouds forming at different altitudes, potentially moving across the planet in complex circulation patterns. On Earth, clouds help distribute thermal energy, create weather events, and even impact chemical cycles. On K2-18b, clouds could similarly mediate temperature differences across the planet, especially given the thick hydrogen envelope, which acts as a powerful greenhouse. By trapping heat and moderating temperature fluctuations, the clouds may maintain relatively stable conditions in the lower atmosphere and in the underlying oceans, which is crucial for any potential life that might exist in those depths. Infrared spectra from Webb indicate variations in the opacity of the atmosphere, suggesting patchy clouds or haze layers, which may include water, methane, or more exotic compounds like hydrogen sulfide condensates. These clouds could rise and dissipate as atmospheric currents circulate heat, creating weather phenomena that are both alien and surprisingly Earth-like in principle. For instance, storms might form when convective currents push moisture-rich gas upward, leading to condensation at cooler layers, much like thunderstorms on Earth. However, the scale and intensity of such storms could dwarf terrestrial systems, given the higher pressures and the potential depth of K2-18b's atmosphere. The presence of clouds also affects the detection of atmospheric molecules. Dense cloud layers can obscure spectral signals, making it more challenging to identify trace gases like methane, carbon dioxide, or DMS. Webb's instruments, however, have the sensitivity to peer through these layers, detecting the composition beneath or analyzing variations caused by light passing through gaps in the clouds. This allows scientists not only to confirm the presence of potential biosignatures, but also to understand how weather and cloud formation impact the distribution and mixing of chemicals throughout the atmosphere. Another fascinating implication of these clouds is their role in planetary energy balance. By reflecting some starlight and absorbing infrared radiation, cloud layers may moderate the planet's thermal environment. This is especially important for K2-18b because, as a Hycean world, its habitability relies on maintaining oceans in a liquid state under the protective hydrogen envelope. Clouds may prevent extreme temperature swings between day and night, ensuring that ocean temperatures remain within ranges that can support microbial life. In essence, clouds act as both a shield and a regulator, stabilizing the conditions required for life to exist over long periods. The chemical composition of clouds can also reveal interactions between the ocean and atmosphere. For instance, water vapor rising from the ocean can condense to form clouds, while methane or other gases released by chemical reactions or hypothetical biological processes could become trapped in these layers, contributing to the overall atmospheric chemistry. These interactions create a dynamic feedback loop where atmospheric circulation, cloud formation, and chemical cycling are interdependent, shaping both climate and habitability. Moreover, Webb's observations hint at the possibility of seasonal variations in cloud coverage. Although K2-18b orbits a red dwarf star, which emits a relatively steady amount of light compared to more massive stars, subtle variations in orbit or axial tilt could create changes in cloud density and weather patterns over time. These variations could influence the distribution of energy, nutrients, and potential chemical biomarkers across the planet, adding complexity to the environment in which hypothetical life forms might exist. Clouds on K2-18b may also be a vehicle for transporting biologically relevant molecules. Just as on Earth, where gases released by marine microorganisms can be carried into the atmosphere and eventually affect the global climate, K2-18b's clouds might carry trace gases like DMS or methane from the underlying oceans into the upper atmosphere. This transport is crucial for remote detection because it allows telescopes like Webb to analyze the chemical fingerprints of the planet, effectively revealing potential life without the need to physically sample the oceans. Clouds and weather systems are important for modeling habitability. Stable cloud layers may protect the oceans from harmful radiation, moderate temperature extremes, and facilitate chemical cycling, all of which are necessary conditions for life. Understanding the patterns, compositions, and dynamics of these clouds gives scientists a window into how the atmosphere interacts with the ocean below, creating environments where microbial or even more complex life could persist over geological timescales. In summary, K2-18b's skies are likely dominated by thick, dynamic clouds that regulate temperature, transport chemicals, and potentially shield the oceans beneath, creating a stable and life-supporting environment. Webb has revealed that the atmosphere is far from static. It is a living system in its own right, with circulation patterns, cloud formation, and chemical interactions that mirror the complexity of Earth's atmosphere in principle, if not in exact form. These clouds do more than shape weather. They may also carry the chemical signs of life into observable layers, making the planet not just a candidate for habitability, but an active laboratory for studying how alien ecosystems might function. K2-18b presents a fascinating paradox when it comes to size and habitability. At roughly 2.6 times the radius of Earth and about 8 times its mass, it is far larger than our planet, placing it in the category of a super-Earth or mini-Neptune. This increased size profoundly influences its gravity, atmosphere, and potential for supporting life. And understanding these factors is essential for evaluating the planet's true habitability. The sheer scale of K2-18b brings both opportunities and challenges for life, creating conditions that are alien, yet not entirely inhospitable. The first consideration is gravity. A larger mass results in stronger surface gravity, which could be 2 to 3 times that of Earth, depending on the planet's density and composition. For hypothetical organisms, this high gravity would impose significant structural constraints. Terrestrial-style life forms as we know them might find it difficult to move or grow in such conditions. However, microbial life or organisms adapted to high-pressure, high-gravity environments could thrive, particularly in the ocean layers beneath the dense atmosphere. Gravity also affects atmospheric retention. K2-18b's strong gravitational pull helps the planet hold on to a thick, hydrogen-rich atmosphere, which is essential for its Hycean classification. Without this atmosphere, liquid oceans could evaporate, and the planet's habitability would be severely compromised. The planet's large size also affects atmospheric pressure. The combination of gravity and a hydrogen-rich envelope results in high pressures at the surface and within the oceans. While these pressures would be extreme by human standards, many forms of microbial life on Earth thrive in high-pressure environments, such as deep-sea trenches, hydrothermal vents, and subglacial lakes. On K2-18b, high pressure may actually stabilize the oceans, keeping them in a liquid state over a wide range of temperatures and preventing rapid boiling or evaporation. This pressure also influences chemical reactions, allowing compounds like methane, carbon dioxide, and water to interact in ways that create energy gradients, a critical requirement for sustaining life. The size of K2-18b also introduces thermal considerations. Larger planets retain internal heat longer than smaller ones because of the greater volume to surface area ratio. This residual heat from planetary formation, combined with radioactive decay, may warm the ocean floor, creating geothermal hotspots analogous to Earth's hydrothermal vents. These hotspots could provide localized energy sources that sustain ecosystems independent of sunlight, a vital consideration for a Hycean world where the oceans are buried beneath hundreds of kilometers of hydrogen-rich atmosphere. The planet's size, therefore, indirectly supports life by maintaining both atmospheric and thermal conditions favorable for habitability. However, the larger radius and mass also pose potential challenges for habitability. For instance, the increased gravity could inhibit the evolution of complex, mobile life as we know it. Terrestrial analogues suggest that larger planets may favor smaller, more compact organisms, particularly in aquatic environments where buoyancy can mitigate gravitational constraints. The immense size could also affect atmospheric circulation. Thicker atmospheres may slow wind patterns or create stratified layers that inhibit mixing. While this could stabilize certain chemical gradients, it might also limit the dispersal of nutrients or gases, potentially affecting the dynamics of any oceanic ecosystems. Another consequence of K2-18b's size is its ability to retain volatiles, such as hydrogen, methane, and water vapor, over geological timescales. Smaller planets often lose their atmospheres to space, particularly light gases like hydrogen. K2-18b's strong gravity ensures that its hydrogen-rich envelope is stable, maintaining the protective atmospheric layer that keeps its oceans liquid. This persistent atmosphere is critical not only for habitability, but also for biosignature detection, since gases released by hypothetical life in the ocean must travel through the thick atmosphere to reach the upper layers where Webb can observe them. In other words, the planet's large size makes it easier to detect potential life from afar, creating a natural observational advantage. Interestingly, K2-18b's scale may also influence ocean chemistry. Larger planets can support deeper oceans with greater pressure at the base, allowing chemical reactions that might not occur in shallower waters. These pressure-enhanced reactions could release nutrients or energy sources critical for microbial ecosystems. The ocean's depth also provides protection from stellar flares and radiation, which is especially important around red dwarf stars known for their flare activity. The combination of size, deep oceans, and thick atmosphere forms a layered defense system, shielding life while maintaining chemical and thermal stability. The size of K2-18b challenges assumptions about the types of habitable worlds that can exist. Traditionally, Earth-sized planets were considered the most likely candidates for life, but K2-18b demonstrates that larger planets with exotic compositions can also support environments conducive to biology. Its strong gravity, thick atmosphere, deep oceans, and retained internal heat all combine to create a world where life might exist under conditions vastly different from terrestrial norms. This expands the search parameters for habitable exoplanets and highlights the diversity of worlds that could support life in the universe. In summary, K2-18b's larger size presents both advantages and challenges for habitability. Strong gravity stabilizes the atmosphere, maintains liquid oceans, and enables the detection of biosignatures, while high pressure and internal heat create energy-rich environments for potential life. At the same time, the gravity and atmospheric dynamics impose constraints on the type of life that could thrive, favoring small, adaptable organisms over complex, mobile creatures. Despite these challenges, the size problem does not preclude habitability. Instead, it reveals an alien yet plausible world where life could persist under conditions entirely unlike Earth's, highlighting the need to think beyond our planetary biases. Human survival on K2-18b presents a scenario that is as fascinating as it is daunting. While the planet shows tremendous potential for life in its oceans, it is utterly inhospitable to humans in its natural state. The combination of a hydrogen-rich atmosphere, crushing gravity, extreme pressures in the oceans, and a lack of breathable oxygen would make any unprotected visit fatal. Even before considering the possibility of alien microbes or chemical hazards, the basic conditions of the planet impose immediate, life-threatening challenges for humans. The first major obstacle is atmospheric composition. K2-18b's atmosphere is dominated by hydrogen, with traces of water vapor, methane, and carbon dioxide. For humans, breathing such an atmosphere is impossible. Hydrogen is not metabolically useful and cannot support respiration. Attempting to inhale even small amounts would displace oxygen in the lungs, leading to asphyxiation. Furthermore, the thick hydrogen envelope presents the danger of explosive reactions in the presence of heat or sparks, making unprotected exposure hazardous. Any human expedition would require pressurized, oxygen-rich suits or habitats similar to the protective gear used in space, but adapted to withstand the additional environmental extremes of K2-18b. Gravity presents another critical challenge. With a surface gravity potentially 2 to 3 times stronger than Earth's, human physiology would be under constant strain. Our muscles, bones, and cardiovascular systems are optimized for Earth's gravity. Prolonged exposure to K2-18b's conditions could lead to severe musculoskeletal damage, heart strain, and reduced mobility. Even basic tasks like walking, lifting, or operating machinery would become extraordinarily difficult. To survive, humans would need artificial environments with controlled gravity, such as floating habitats or advanced exoskeletons, to mitigate these stresses and maintain functionality. The surface conditions themselves further limit human survival. K2-18b likely lacks exposed solid ground in many areas, instead featuring deep oceans beneath a dense atmosphere. The ocean depths, potentially hundreds of kilometers thick, would create pressures far exceeding the limits of any human-engineered submersible. Even the planet's upper atmospheric layers, where pressures are lower, would remain hostile due to extreme chemical composition and high hydrogen density. Colonization would therefore likely require floating platforms or orbital stations that allow humans to interact with the planet indirectly, rather than attempting to inhabit the surface or ocean. Temperature and radiation add additional complexity. While K2-18b may have moderate ocean temperatures suitable for life, the lack of Earth-like insulation and the planet's orbit around a red dwarf star could expose humans to unpredictable stellar flares or radiation bursts. Red dwarfs are known for their intense magnetic activity, which can produce high-energy radiation that would penetrate protective habitats if not properly shielded. Advanced materials and radiation shielding would be essential for any attempt to establish long-term human presence. Energy sources for human habitation would also need to be self-contained. Unlike Earth, K2-18b does not provide familiar resources like breathable air, plant-based food, or terrestrial water. Any colony would require closed-loop life support systems, recycling air, water, and nutrients while generating energy independently, perhaps through nuclear reactors or solar arrays adapted to the red dwarf's spectrum. The logistics of maintaining such systems hundreds of light years away from Earth would be immense, making the prospect of colonization a long-term, technologically extreme challenge. Despite these obstacles, human curiosity and ingenuity make the concept of interacting with K2-18b intriguing. Remote exploration via robotic probes could allow us to study its oceans, atmospheric chemistry, and potential biosignatures without ever risking human life. Drones or autonomous submarines could descend into the oceans, analyze chemical gradients, and even attempt to detect signs of life directly. Orbital platforms could monitor weather patterns, cloud dynamics, and gas fluxes, building a detailed picture of the planet's environment. These tools could offer insights that would inform future human habitation scenarios, even if direct colonization remains impossible with current technology. Speculating about human adaptation to K2-18b opens fascinating possibilities. Advanced genetic engineering or cybernetic augmentation could, in theory, allow humans to tolerate higher gravity or hydrogen-rich atmospheres, though this remains firmly in the realm of science fiction for now. Colonization strategies might also focus on creating biodomes or artificial floating habitats that simulate Earth-like conditions while leveraging the planet's resources for energy and chemical experiments. For example, hydrogen-rich atmospheres could theoretically be used as fuel in controlled reactions, and the deep oceans could serve as reservoirs for water once purified and managed in pressurized systems. In essence, while humans could not survive on K2-18b in its natural state, the planet presents opportunities for indirect exploration, robotic study, and perhaps, in the distant future, engineered habitats. Its alien conditions highlight the resilience required for life as we know it to exist elsewhere, and they underscore the importance of understanding extremophile life, planetary chemistry, and adaptive technologies that could allow humans to observe and interact with such worlds safely. K2-18b challenges our assumptions about habitability and pushes the boundaries of what it means to live on a planet, revealing a world where alien ecosystems could thrive in conditions utterly hostile to human physiology. The question of what forms of life could exist on K2-18b is both tantalizing and profoundly complex. Given the planet's unique environment, a hydrogen-rich atmosphere, deep global oceans, and moderate but stable temperatures, the most likely candidates for life are microbial organisms. Microbes are the most adaptable and resilient life forms, capable of surviving extreme pressures, low or high temperatures, and chemical environments that would be hostile to complex life. On Earth, we find microbes thriving in deep-sea hydrothermal vents, subglacial lakes, and acidic hot springs, environments once thought uninhabitable. By analogy, K2-18b's oceans could host vast populations of extremophilic microbes, potentially forming the foundation of a rich alien ecosystem. The composition of the planet's atmosphere provides additional clues. The presence of water vapor, methane, carbon dioxide, and possibly dimethyl sulfide, DMS, suggests active chemical processes beneath the clouds. On Earth, these molecules are often linked to biological activity. For example, DMS is almost exclusively produced by microbial life in the oceans. Methane can be a product of both biological and geological activity, but when observed alongside other compounds like DMS, it strongly hints at biology. If life exists on K2-18b, it is likely chemically active and metabolically diverse, exploiting the chemical gradients in the deep ocean to obtain energy, much like Earth's chemosynthetic microbes. Beyond individual microbes, K2-18b could support complex oceanic ecosystems. While the thick hydrogen atmosphere and extreme pressures make the evolution of large, mobile life unlikely, microbial communities could form intricate networks. Biofilms, mats, and colonies could exist around hydrothermal vents or in regions with higher chemical availability. These ecosystems could operate similarly to Earth's deep-sea vent communities, where energy derived from chemical reactions, rather than sunlight, sustains a web of interacting species. In theory, some microbes could even cooperate or compete in ways that give rise to higher-order structures, perhaps clusters or layered communities optimized to extract energy from their environment. Speculation about more advanced life forms is far more uncertain. Given the extreme pressures, lack of sunlight, and thick atmosphere, complex multicellular organisms would face severe evolutionary constraints. Any hypothetical advanced life would need to adapt to constant high pressure, a dense medium, and limited energy sources. While it is tempting to imagine alien octopus-like creatures or intelligent aquatic beings, the constraints of the environment make microbial or small multicellular life far more plausible. Evolutionary pathways might favor simplicity, robustness, and efficiency rather than complexity or mobility. However, given enough time and chemical energy, the possibility of more sophisticated life cannot be entirely ruled out. Energy sources on K2-18b's ocean floor would likely drive biological productivity. Hydrothermal vents, chemical gradients, and interactions between hydrogen, methane, and other molecules could create localized niches where life thrives. These regions might serve as hotspots of biodiversity, with microbes forming symbiotic relationships or metabolic networks that maximize energy extraction. Even if life remains microscopic, the sheer volume of the oceans, potentially hundreds of kilometers deep and covering the entire planet, means that the total biomass could be enormous, potentially exceeding Earth's oceanic biomass, simply due to the scale of the environment. The thick hydrogen atmosphere also affects life in unique ways. Rising gases could transport molecules like DMS from the oceans into the upper atmosphere, potentially making biological activity detectable from Earth. This transport suggests that life on K2-18b, even if confined to subsurface oceans, could leave chemical fingerprints on a planetary scale, bridging the gap between alien biospheres and remote observation. These signals provide the best opportunity for detecting life, as direct exploration of the oceans would be technologically prohibitive. Another intriguing possibility is that life on K2-18b could exhibit chemical adaptations distinct from Earth-based biology. While Earth life relies on carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, CH-NOPs in familiar forms, the unique pressures, chemical composition, and oceanic depth of K2-18b may allow for alternative biochemistries. For instance, life might utilize hydrogen-rich compounds more extensively, develop pressure-stabilized proteins, or exploit chemical energy sources unavailable on Earth. This does not preclude the presence of carbon-based life, but it does suggest that alien organisms could appear fundamentally different at a molecular level. In essence, the most plausible forms of life on K2-18b are microbes and microbial ecosystems, potentially forming complex networks that exploit chemical energy in the oceans. Larger multicellular organisms, while theoretically possible, are unlikely given the extreme environmental constraints. Yet even these microscopic forms of life could have a planetary scale impact, generating gases and chemicals that rise into the atmosphere, providing detectable biosignatures for telescopes like JWST. The mere existence of such life would fundamentally expand our understanding of where and how life can thrive, demonstrating that habitable environments do not need to resemble Earth exactly. K2-18b embodies the tantalizing possibility of life that is both alien and detectable. Its oceans, atmosphere, and chemical interactions form a potentially self-sustaining biosphere, hidden beneath layers of clouds but broadcasting hints of its presence through molecules like DMS and methane. The diversity and adaptability of potential life forms challenge our assumptions, forcing us to broaden our concept of habitability and consider worlds where life could flourish in conditions that are extreme, alien, yet scientifically plausible. Despite the excitement surrounding the 99.7% probability of life on K2-18b, scientists approach this figure with careful skepticism. The claim is statistical, not observational, and relies on modeling, assumptions, and indirect measurements rather than direct detection of living organisms. While JWST has revealed extraordinary details, such as water vapor, methane, carbon dioxide, and potential DMS signatures, interpreting these molecules as definitive proof of life involves numerous uncertainties. First, there is the challenge of false positives. Many molecules associated with life on Earth can also form through purely abiotic processes. Methane, for example, can emerge from geological reactions such as serpentinization, where water interacts with certain minerals under high pressure and heat. Similarly, hydrogen-rich atmospheres can foster chemical pathways that produce complex organic molecules without any biological intervention. Even dimethyl sulfide, while highly suggestive of biological activity due to its rarity in abiotic contexts, could theoretically arise under unknown chemical conditions unique to K2-18b's environment. Therefore, scientists must consider all possible non-biological explanations before assigning a probability of life. Second, the interpretation of atmospheric data is inherently complex. Webb observes the planet by analyzing the starlight that filters through its atmosphere during transits. This light carries spectral signatures of molecules, but extracting accurate abundances from these spectra involves sophisticated models that account for temperature, pressure, cloud coverage, and chemical interactions. Any error in these models can significantly affect the inferred likelihood of habitability. For instance, clouds and hazes in the upper atmosphere can obscure or distort chemical signals, potentially exaggerating or underestimating the presence of key molecules. Scientists must navigate significant observational noise and modeling uncertainties, making definitive claims about life extremely difficult. Third, there is the issue of environmental context. While K2-18b has oceans and a hydrogen-rich atmosphere conducive to life, we cannot yet confirm surface or oceanic conditions directly. Estimates of temperature, pressure, and chemical gradients are based on modeling, and even small variations could dramatically alter the planet's habitability. For example, if the deep oceans are too acidic, lack sufficient chemical energy, or have extreme salinity, life as we know it might struggle to survive,
despite the presence of water and organic molecules in the atmosphere. Thus, physical and chemical constraints may reduce the probability of life, even if the atmosphere seems promising. Additionally, the interpretation of DMS, the molecule that greatly influences the 99.7% figure, is itself uncertain. While DMS is almost exclusively produced by biology on Earth, the potential for alien chemistry to generate DMS or similar sulfur compounds cannot be entirely ruled out. K2-18b's hydrogen-rich, high-pressure environment is fundamentally different from Earth's oceans, so molecules that are biologically exclusive here might arise through unknown geochemical processes there. Until these possibilities are better understood, attributing DMS detection solely to life carries a degree of uncertainty.
Another challenge is the probabilistic nature of the claim itself. The 99.7% figure is derived from models combining chemical abundance, planetary environment, and habitability likelihoods, essentially creating a weighted estimate rather than direct evidence. While this statistical approach is scientifically rigorous, it is sensitive to input assumptions. Small changes in model parameters, such as atmospheric chemistry, temperature profiles, or assumed ocean composition, could dramatically alter the probability. As a result, scientists emphasize that the number should be interpreted as a highly suggestive estimate, not a guarantee of life. The context of exoplanetary research also tempers enthusiasm. K2-18b is only one of thousands of confirmed exoplanets, and while it appears uniquely promising, the field has previously encountered cases where initial optimism was tempered by further study. Early interpretations of spectral signatures, temperature estimates, or habitability models often change as more sophisticated data becomes available. This iterative nature of science requires caution. Even if K2-18b seems like the most habitable exoplanet detected to date, the probability of life must be viewed as provisional and subject to revision. Finally, there are technological limitations. JWST provides unmatched sensitivity, but it still observes from 120 light-years away, with no direct access to the planet. Measurements depend on indirect inference, such as analyzing light passing through the atmosphere or reflected by clouds. Any instrumental noise, calibration errors, or unforeseen atmospheric effects could skew results, complicating the interpretation of potential biosignatures. In summary, scientists remain cautious about the 99.7% figure because it depends on indirect measurements, modeling assumptions, and interpretation of molecules that might not be exclusively biological. While K2-18b is exceptionally promising, the claim is probabilistic rather than definitive, reflecting the exciting but uncertain frontier of exoplanetary science. It represents a convergence of tantalizing evidence rather than conclusive proof, reminding us that the search for life is as much about rigorous skepticism as it is about discovery. The future of research on K2-18b is as exciting as the initial discoveries themselves, with the James Webb Space Telescope positioned to play a central role in further characterizing this remarkable world. JWST's first observations already revealed water vapor, methane, carbon dioxide, and hints of dimethyl sulfide, but these are only the first glimpses of a far more complex planetary system. To truly understand K2-18b's potential for life, astronomers are planning a series of follow-up studies designed to refine atmospheric models, detect additional biosignatures, and probe the planet's environment with unprecedented precision. One of the primary goals is repeated transit spectroscopy. By observing multiple transits, moments when K2-18b passes in front of its host star, JWST can gather more detailed spectral data across different wavelengths. This repeated observation allows scientists to confirm initial findings, reduce measurement uncertainties, and detect temporal changes in the atmosphere. Clouds, storms, or even seasonal shifts in chemical abundances could influence the planet's spectral signatures,
so repeated observations are crucial for distinguishing between transient phenomena and persistent atmospheric features. Such studies will help determine whether molecules like DMS are consistently present or merely transient, providing stronger evidence for or against biological activity. Another area of focus is high-resolution spectroscopy. While initial observations provided broad chemical fingerprints, higher resolution measurements can pinpoint the exact concentrations of gases in the atmosphere. This precision is vital for identifying subtle biosignatures and understanding chemical interactions. For example, measuring the ratios of methane to carbon dioxide or tracing isotopic signatures could help distinguish between biological and abiotic sources. By teasing out these details, astronomers hope to build a more comprehensive chemical map of K2-18b's atmosphere, revealing the complex interplay of molecules that could sustain life. JWST also plans to observe K2-18b in infrared thermal emissions, rather than solely relying on transit spectroscopy. By measuring the planet's emitted heat, scientists can infer temperature distributions across different atmospheric layers. This provides insight into weather patterns, cloud formation, and energy transport, which are critical for modeling the planet's surface and ocean conditions. Understanding thermal dynamics is also key to assessing habitability because temperature gradients influence ocean circulation, chemical availability, and potential energy sources for life. In addition, astronomers aim to study vertical atmospheric structure. K2-18b's thick hydrogen-rich envelope likely exhibits layers of varying pressure, temperature, and composition. By analyzing absorption at different wavelengths, JWST can probe multiple altitudes, revealing how gases are distributed from the upper atmosphere down to near the ocean surface. This vertical profiling is essential for assessing whether molecules associated with life, like DMS or methane, can migrate from the ocean to detectable levels in the upper atmosphere. It also helps constrain cloud heights, atmospheric mixing rates, and the potential for habitable niches beneath the clouds. Future observations will also explore planetary phase curves, which track how the planet's brightness changes as it orbits its star. These curves can provide information about reflectivity, cloud coverage, and surface or ocean composition. If different regions of K2-18b exhibit varying reflectivity or thermal output, scientists could identify zones where conditions are more favorable for life. This data complements spectroscopic measurements, offering a three-dimensional view of the planet's environment and the dynamic processes occurring within its atmosphere and oceans. Collaboration with other observatories is another key aspect of the ongoing study. While JWST provides unprecedented infrared sensitivity, combining its data with other telescopes, such as ground-based extremely large telescopes or the upcoming Nancy Grace Roman Space Telescope, can extend observations to other wavelengths, improve signal-to-noise ratios, and validate findings. This multi-instrument approach is crucial for cross-checking biosignature detections and reducing the likelihood of false positives. By leveraging multiple technologies, scientists hope to construct a more robust, multi-dimensional understanding of K2-18b. Moreover, JWST's future studies may include comparative planetology. By observing other Hycean candidates or planets with similar masses and orbital properties, astronomers can contextualize K2-18b's features. Comparing atmospheric composition, cloud dynamics, and potential biosignatures across multiple worlds allows researchers to identify patterns or anomalies, improving confidence in identifying life and understanding the processes that make planets habitable. This comparative approach can also refine models, revealing whether K2-18b is truly exceptional or part of a broader class of potentially life-bearing worlds. In addition to observational work, JWST's data will inform theoretical and computational modeling. By integrating spectral measurements, thermal profiles, and chemical distributions into sophisticated models, scientists can simulate potential ocean chemistry, atmospheric circulation, and energy cycles on K2-18b. These models can test hypotheses about life's feasibility, chemical pathways, and long-term environmental stability. Repeated observational data from JWST will allow these models to be refined iteratively, increasing confidence in predictions about habitability and potential biosignature presence. Finally, future Webb observations could guide mission planning for next-generation exploration. While physical probes to K2-18b remain beyond current technological capabilities, detailed atmospheric and oceanic data could inform the design of hypothetical robotic missions or inform searches for similar, closer exoplanets. Understanding how to detect biosignatures remotely, analyze thick atmospheres, and interpret chemical signals sets a precedent for the broader search for life across the galaxy. In summary, the next phase of K2-18b research involves a multifaceted approach combining repeated high-resolution spectroscopy, thermal emission studies, vertical profiling, phase curve analysis, and collaborative observations across instruments. These efforts aim to reduce uncertainties, confirm biosignatures, and build a detailed understanding of the planet's atmosphere, oceans, and habitability. JWST's future observations will push the boundaries of what we can know about alien worlds, moving K2-18b from a tantalizing candidate to a thoroughly characterized planet, potentially revealing whether this distant ocean world truly harbors life. K2-18b exists within an expanding catalogue of exoplanets that intrigue scientists and the public alike, yet it occupies a distinct position among potentially habitable worlds. When compared to systems like TRAPPIST-1, which boasts 7 Earth-sized planets orbiting a red dwarf star, K2-18b stands out due to its unique combination of size, atmospheric composition, and potential habitability, while also highlighting the diversity of worlds that may host life. The TRAPPIST-1 system has captured widespread attention because multiple planets reside within the star's habitable zone, the range of distances where liquid water could theoretically exist on a planet's surface. These planets are roughly Earth-sized, which initially made them seem like ideal candidates for life. However, TRAPPIST-1's planets orbit extremely close to their host star, exposing them to intense stellar activity, including flares and high-energy radiation. These conditions could strip atmospheres, particularly hydrogen-rich envelopes, leaving planets vulnerable to extreme surface conditions. In contrast, K2-18b orbits its star at a distance that allows it to retain a thick hydrogen-rich atmosphere, providing insulation and moderating temperature fluctuations, which is crucial for maintaining liquid water oceans over geological timescales. This makes K2-18b, despite being larger, more resilient in terms of atmospheric retention and stability, potentially creating a more consistent environment for life. Size is another differentiating factor. K2-18b is roughly 2.6 times the radius of Earth and about 8 times its mass, classifying it as a super-Earth or mini-Neptune. TRAPPIST-1 planets, by contrast, are closer to Earth's size, which means their gravity is weaker and they are less capable of holding onto thick atmospheres over long periods. While smaller size may favor the evolution of terrestrial-like life, it also makes these planets more vulnerable to atmospheric erosion. K2-18b's larger size allows for high-pressure oceans and strong gravity, which, while hostile to humans, could be ideal for microbial life and provide a stable environment for complex chemical processes. Atmospheric composition further separates K2-18b from TRAPPIST-1 planets. Webb's observations revealed a hydrogen-rich envelope containing water vapor, methane, carbon dioxide, and potentially DMS. This combination of gases indicates a chemically active environment with plausible biosignature markers. By comparison, TRAPPIST-1 planets are more difficult to characterize due to their smaller size and close proximity to a flare-prone star, making atmospheric retention uncertain. The lack of confirmed thick atmospheres on TRAPPIST-1 planets means that even if water exists, these worlds may not have the chemical complexity or protective envelope
that K2-18b provides, potentially limiting habitability. Moreover, K2-18b is the first Hycean world identified as a serious candidate for life, a category absent in the TRAPPIST-1 system. Hycean planets, with hydrogen-dominated atmospheres and deep oceans, present a fundamentally different model for habitability than terrestrial-like worlds. While TRAPPIST-1 planets may have thin atmospheres and surface oceans, they are exposed to radiation and extreme stellar variation, whereas K2-18b's thick atmosphere and internal heat provide environmental buffering, which may create more stable and life-friendly conditions beneath the clouds. This highlights an emerging principle. Habitability may not require Earth-like conditions, but rather a combination of environmental stability, chemical diversity, and energy availability, all of which K2-18b appears to possess. Distance and observational accessibility also distinguish K2-18b. Located about 120 light-years away in the constellation Leo, it is close enough for Webb to perform detailed spectroscopy, detect atmospheric gases, and identify potential biosignatures. While the TRAPPIST-1 system is closer, roughly 40 light-years away, its planet's smaller size and thinner atmospheres make detection of complex molecules more challenging. K2-18b's thick envelope amplifies chemical signals, making the presence of life-related molecules easier to detect with current instruments, which is why it has garnered such attention as a leading candidate for hosting life. Energy sources also play a role in comparative habitability. K2-18b's deep oceans may receive heat from internal geothermal activity, chemical gradients, and tidal forces, creating energy-rich niches for life, independent of stellar radiation. TRAPPIST-1 planets, in contrast, are more dependent on starlight for surface energy, and frequent flares could disrupt photosynthesis-like processes or strip atmospheres. K2-18b's independent energy sources suggest that life could persist even under variable stellar conditions, giving it an advantage in terms of potential biomass sustainability.
It is important to note that TRAPPIST-1 is not irrelevant to the search for life. It demonstrates that compact, multi-planet systems around red dwarfs may be abundant and offer multiple laboratories for studying planetary habitability. However, the specific combination of traits on K2-18b, size, atmosphere, chemical richness, and thermal stability makes it uniquely suited for detailed study. It is a world where chemical fingerprints of life may be directly observable rather than inferred from thin atmospheres or uncertain environmental conditions. In summary, K2-18b occupies a distinct niche among promising exoplanets. While TRAPPIST-1 highlights the potential of Earth-sized planets in habitable zones, K2-18b demonstrates that larger worlds with hydrogen-rich envelopes can also sustain life-friendly conditions, possibly more reliably than smaller, radiation-exposed planets. Its thick atmosphere, deep oceans, internal energy sources, and detectable biosignatures combine to make it a compelling target, suggesting that life may be possible on planets vastly different from Earth. K2-18b and TRAPPIST-1 together illustrate the diversity of habitable environments in our galaxy, expanding the criteria for where and how life could exist, and emphasizing that habitability is not solely determined by size or distance from a star, but by a complex interplay of chemistry, energy, and environmental stability. The discovery of K2-18b and the potential indicators of life in its atmosphere fundamentally reshape the search for biosignatures across the galaxy, offering both a roadmap and a cautionary tale for astronomers, astrobiologists, and planetary scientists. Biosignatures, chemical, physical, or structural indicators of life, have long been a central focus of astrobiology. Until recently, most efforts concentrated on Earth-like planets, assuming that habitability required terrestrial conditions, oxygen-rich atmospheres, moderate temperatures, and rocky surfaces. K2-18b challenges this narrow paradigm, demonstrating that life may thrive under entirely alien conditions, such as hydrogen-dominated atmospheres and deep, high-pressure oceans. The detection of molecules like water vapor, methane, carbon dioxide, and dimethyl sulfide, DMS, on K2-18b illustrates a critical shift in the methodology of biosignature searches. Traditionally, scientists focused on gases like oxygen or ozone, which are produced predominantly by photosynthetic organisms on Earth. However, the study of K2-18b shows that alternative life-supporting chemistries may exist. Hydrogen-rich environments, for instance, can sustain life forms that do not rely on sunlight or oxygen, but instead utilize chemical energy derived from molecules like methane or sulfur compounds. This broadens the spectrum of biosignatures to include molecules that were once considered ambiguous or secondary. Future searches must therefore account for planet-specific chemistry, emphasizing the need for flexible, context-dependent models of life detection. K2-18b also highlights the importance of atmospheric observables as a primary tool in the search for life. Direct exploration of exoplanetary surfaces is currently impossible, but by analyzing the composition, structure, and dynamics of an atmosphere, astronomers can infer the potential presence of life indirectly. For instance, the presence of DMS in K2-18b's upper atmosphere, rising from the oceans below, suggests a planet-wide chemical flux that could be biologically generated. Detecting such signatures remotely, using advanced instruments like JWST or future telescopes, transforms exoplanets into laboratories for life detection, where careful spectral analysis can reveal the fingerprints of alien biochemistry across hundreds of light-years. Another significant implication of K2-18b's discovery is the need to re-evaluate planetary classifications when searching for life. Hycean worlds, large, hydrogen-rich planets with global oceans, were largely theoretical until K2-18b. Their emergence as viable candidates suggests that the traditional Earth analog model may overlook a substantial fraction of habitable worlds. The galaxy likely hosts thousands, if not millions, of Hycean-type exoplanets, many of which could exhibit detectable biosignatures. This realization shifts priorities in exoplanetary surveys, emphasizing the need to target planets that were previously dismissed as too large, gaseous, or un-Earth-like. Moreover, K2-18b underscores the value of multidisciplinary approaches in biosignature detection. Chemistry, physics, planetary geology, and astrobiology must intersect to interpret signals accurately. For instance, understanding whether methane arises from biological activity or geochemical processes requires modeling planetary interiors, ocean chemistry, and atmospheric dynamics. Similarly, detecting DMS or other organic molecules necessitates careful consideration of abiotic pathways, potential observational biases, and instrument limitations. K2-18b exemplifies how successful biosignature identification relies on integrating diverse data streams, from high-resolution spectra to stellar activity monitoring, to construct a coherent picture of habitability. The search for biosignatures also emphasizes the importance of contextual verification. Observing a single molecule in isolation is rarely conclusive. Instead, scientists seek co-occurring molecular patterns or anomalies that suggest non-equilibrium chemistry. K2-18b's combination of water vapor, methane, carbon dioxide, and possible DMS is compelling precisely because it forms a suite of chemical indicators that are unlikely to arise purely from abiotic processes. This multifaceted approach increases confidence in interpreting potential life signals and serves as a blueprint for identifying promising exoplanets in future surveys. K2-18b's discovery has broader philosophical and scientific implications as well. If life is confirmed, or even strongly suggested, on a planet so different from Earth, it would indicate that life may be far more adaptable and widespread than previously imagined.
This would justify the allocation of significant observational resources to search for life on non-Earth-like worlds, expanding the frontiers of astrobiology. Moreover, it challenges humanity to redefine our criteria for habitability, moving beyond a narrow Earth-centric view to embrace diverse planetary environments where life could exist in forms we have yet to fully comprehend. The lessons from K2-18b extend to future mission planning. Detecting biosignatures remotely requires instruments capable of analyzing subtle spectral features with extreme sensitivity. JWST has demonstrated the feasibility of such observations, but future telescopes, both ground-based and spaceborne, will need to push the boundaries further. Missions like the Nancy Grace Roman Space Telescope, the Extremely Large Telescope, and concepts for next-generation space observatories are being designed with the capacity to detect molecular signatures, atmospheric dynamics, and surface interactions on an unprecedented scale. K2-18b thus serves as a practical target, a testbed for refining techniques and validating models that will be applied to countless exoplanets across the galaxy. Finally, the study of K2-18b reinforces the interconnectedness of habitability factors. It is not enough for a planet to reside in a habitable zone. Its atmospheric composition, ocean chemistry, internal heat, cloud dynamics, and potential biosignature transport mechanisms all interact to create conditions conducive to life. This holistic view ensures that the search for life is systematic, rigorous, and adaptable, informed by both theoretical frameworks and empirical evidence. K2-18b exemplifies how complex, multi-layered analysis is necessary to distinguish truly promising biosignature candidates from planets that may appear superficially habitable but lack the sustaining conditions for life. In summary, K2-18b has redefined the search for biosignatures. It demonstrates that life may exist under hydrogen-rich, high-pressure conditions, that molecules like DMS can serve as powerful indicators, and that multifaceted observation strategies are essential for accurate interpretation. Its discovery broadens the range of potentially habitable planets, informs future telescope design, and challenges Earth-centric assumptions about life. By studying K2-18b, scientists gain not only a potential glimpse of alien biology, but also a framework for understanding life in the galaxy more broadly, a roadmap for identifying where, how, and under what conditions life might exist far beyond our solar system. The prospect that life might exist on K2-18b carries profound implications that ripple across science, philosophy, and human consciousness. Even before direct confirmation, the very possibility challenges our understanding of life's universality and forces a reconsideration of our place in the cosmos. Philosophically, the existence of extraterrestrial life, particularly on a world vastly different from Earth, would fundamentally alter the narrative of humanity as the singular pinnacle of biological complexity. It would suggest that life is not an anomaly confined to a narrow set of conditions, but rather a natural and potentially widespread phenomenon, capable of emerging under circumstances that once seemed inhospitable. From a scientific standpoint, the discovery of life on K2-18b would be nothing short of revolutionary. It would provide the first empirical example of life evolving independently of Earth, confirming that biology is not an Earth-centric accident, but a natural outcome of chemistry and planetary processes. Such a finding would validate theories of abiogenesis occurring under diverse conditions and offer a second data point to study evolutionary mechanisms. Scientists would gain the unprecedented opportunity to examine alternative biochemistries, metabolic strategies, and ecological interactions, illuminating how life adapts to extreme environments, harnesses energy, and maintains homeostasis under pressures, hydrogen-rich atmospheres, and global oceans unlike anything on Earth. The impact on astrobiology and planetary science would be immediate and profound. A confirmed biosphere on K2-18b would validate the search for life on other Hycean planets, super-Earths, and non-terrestrial worlds,
shifting research priorities away from solely Earth analogues. It would also refine the criteria used to define habitability, emphasizing chemical energy, environmental stability, and biosignature transport over familiar Earth-like conditions. The confirmation of life elsewhere would provide a template for understanding biosignature generation, detection, and interpretation, greatly enhancing the efficiency of future missions to distant exoplanets. On a broader scale, such a discovery would challenge long-standing philosophical questions about uniqueness, purpose, and meaning. Humanity has long grappled with the question of whether we are alone in the universe. Evidence of life on K2-18b would force a re-evaluation of human exceptionalism, inviting us to see ourselves as part of a broader biological continuum rather than the sole product of chance in a vast, otherwise lifeless cosmos. The realization that life can flourish in alien oceans under alien skies could inspire new philosophical frameworks, expanding our understanding of ethics, responsibility, and the stewardship of life on Earth in the context of a potentially populated galaxy. The very notion of life existing independently from Earth would generate global discourse on humanity's role in the universe and our moral obligations toward other life forms, even if they are microbial or highly alien in nature. Practical scientific considerations would emerge as well. The discovery would trigger intensive efforts to analyze and characterize alien life safely, given the unknown risks associated with extraterrestrial microbes. Planetary protection protocols, quarantine measures, and remote sensing strategies would become even more critical to avoid contamination, both of Earth and of K2-18b's biosphere. The discovery would also spur investment in advanced telescopes, spectroscopy, and potential robotic missions aimed at understanding life's distribution, environmental niches, and evolutionary pathways beyond our planet. The confirmation of life on K2-18b would also have profound implications for humanity's long-term perspective on survival and colonization. It would highlight the vast possibilities for life beyond Earth, while simultaneously demonstrating the challenges inherent in inhabiting alien worlds. The knowledge that life can thrive under extreme conditions might inspire bioengineering, synthetic biology, and new technologies for human adaptation to environments previously considered uninhabitable. It could also deepen interest in space exploration, fostering a sense of cosmic connection and shared destiny with life beyond Earth. In scientific terms, finding life on K2-18b would allow comparisons between independently evolved biospheres, providing insight into convergent and divergent evolutionary strategies. Questions such as the universality of cellular structures, energy utilization, and the role of specific molecules in metabolic pathways could be addressed, offering a second, independent dataset for biology. It would also provide a foundation for understanding how life may emerge elsewhere in the galaxy, influencing estimates of life's abundance, diversity, and resilience under varying planetary conditions.
The societal impact would extend beyond academia. Media, education, and public consciousness would be transformed by the recognition that life exists on a distant world. It would spark imagination, curiosity, and debate across generations, encouraging global collaboration in space science, ethics, and policymaking. Humanity's perspective on Earth, our environment, and our collective responsibility could evolve, reinforced by the knowledge that life is neither unique nor confined to our own planet. Ultimately, the discovery of life on K2-18b would be both a scientific triumph and a profound cultural milestone. It would answer one of humanity's oldest questions while simultaneously raising new ones about the diversity, adaptability, and meaning of life. It would challenge us to rethink everything from planetary science and biology to philosophy and ethics, while opening a new chapter in our quest to understand the universe. Even the mere possibility that microbial ecosystems or complex oceanic life exist beneath K2-18b's clouds ignites the imagination, reminding us that the cosmos may be teeming with life, waiting for humanity to uncover its secrets. As we look out into the night sky, the discovery of K2-18b invites a sense of awe and anticipation unlike any other in human history. Here is a world 120 light-years away, with deep oceans beneath a thick, hydrogen-rich atmosphere, and molecules in its skies that whisper the possibility of life. It is a planet that challenges our understanding of habitability, biology, and what it means to be alive. Every new observation, every spectral line, every hint of a chemical imbalance could be a signal from an alien biosphere, quietly thriving under clouds far beyond our reach. The enormity of this possibility forces us to pause and consider. If life exists there, even at a microbial scale, it represents the first concrete proof that Earth is not unique, that biology is a cosmic phenomenon rather than a planetary accident. The mystery of K2-18b is compounded by the limits of our perception. We cannot step on its surface, swim its oceans, or breathe its atmosphere. Our understanding is derived from light filtered through clouds and atoms, interpreted by sensors and complex models. Yet, in this indirect way, we are approaching knowledge that would have been unimaginable mere decades ago. JWST acts as our window, allowing us to peer across vast interstellar distances, translating faint signals into the tantalizing language of molecules, chemistry, and potential biology. Each discovery is a step closer to answering one of humanity's oldest and most profound questions. Are we alone? The implications of confirming life on K2-18b extend beyond science. They challenge our philosophical frameworks, our cultural narratives, and our sense of identity. Humanity has long considered itself alone, perched on a tiny planet in a vast, silent universe. K2-18b could prove that this silence is an illusion, that life finds a way even under alien skies and extreme conditions. Such a realization would reshape our understanding of purpose, uniqueness, and the potential for intelligence elsewhere in the cosmos. It would redefine what it means to be a life-bearing planet, and perhaps even what it means to be human, knowing that our story is part of a much larger interstellar tapestry. Yet, the mystery is far from resolved. The 99.7% figure is a tantalizing estimate, not a certainty. Dimethyl sulfide, methane, and water vapor are hints, not confirmations. The oceans beneath K2-18b's clouds remain inaccessible, and the planet's size, pressure, and atmosphere present formidable challenges to life as we know it. Each new observation raises as many questions as it answers, and the edge of discovery is as thrilling as it is elusive. Are these molecules a testament to thriving alien ecosystems, or are they the result of complex chemistry unconnected to life? Will future Webb observations clarify the picture, or reveal yet more enigmatic behavior? This uncertainty, paradoxically, is part of the allure. K2-18b exemplifies the essence of scientific exploration, the pursuit of answers in the face of the unknown. It reminds us that discovery is not merely about certainty, but about curiosity, rigor, and imagination. Every photon captured by JWST carries the potential to rewrite textbooks, to redefine our cosmic context, and to illuminate the broader question of life in the universe. As we reflect on K2-18b, the question remains hanging in the vast expanse between stars. Are we truly on the cusp of the greatest discovery in human history? Could this distant world, with its alien oceans and hydrogen skies, be the first proof that life is not a singular miracle, but a cosmic inevitability? Or will it remain an enigmatic planet, whispering possibilities we may never fully comprehend? The answer lies in the interplay of observation, analysis, and time, and it is a question that may define our generation. In the end, K2-18b challenges us not only to look outward, but to look inward, to consider what life means, how rare or common it might be, and what our responsibility is as conscious observers in a universe potentially teeming with living worlds. It invites us to continue the search, to push the boundaries of technology and imagination, and to embrace the mystery with both scientific rigor and wonder. Whether or not we ever confirm life on K2-18b, its existence reminds us that the universe is larger, stranger, and more full of possibility than we have ever dared to imagine. So as you gaze up at the night sky tonight, remember, somewhere out there, 120 light-years away in the constellation Leo, a Hycean world drifts quietly through the cosmos, and with it comes the promise that we may be on the edge of discovering life beyond Earth, the greatest revelation humanity could ever witness. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.